Welcome, friends. My name is Susan Davidson. I'm the Weiss Professor of Computer and Information Science at the University of Pennsylvania School of Engineering and Applied Science. I'm your host of Penn Engineering's Innovation and Impact podcast. Our podcast shares insights from some of the leading experts from around the world who are Penn and Penn Engineering faculty and researchers. They are bringing to you the latest breakthroughs and innovations in science, technology, and medicine. Today, we're continuing our conversation about artificial intelligence. I am joined in the studio by three experts in AI in their respective fields within Penn. First, we have Chris Callison-Burch. Chris is an associate professor of computer and information science in Penn Engineering. We also have Surbhi Goel. Surbhi is relatively new to Penn Engineering and has joined our faculty as the Magerman turned assistant professor of computer and information science. And finally, we have Cesar de la Fuente. Cesar has many appointments within Penn and is a presidential assistant professor in 5 departments across 3 schools. So let me start with a question to Chris. In just the few short months since we last met, we've seen so many new advances in AI's impact on everything from finance, education, healthcare, transportation, you name it. With these new developments and its rapid growth, how would you summarize the current state of AI?
So since last time we spoke, there's been an enormous investment in artificial intelligence across academia and especially within industry. We've seen everything from Amazon's $4 billion investment in Anthropic to Google and DeepMind remerging to really focus the company on generative AI, to continued breakthroughs from OpenAI, including their latest text-to-video Sora model. So all of these things are really astounding, and I feel like we're still actually at the very infancy of how this is going to affect industry and the world, and it'll probably be a few more years before we start to see these investments having the high impact across all sectors that I anticipate that they will eventually have. So one of the things that I'm most excited by is not just these giant tech companies or the chip makers like NVIDIA really having these splashy numbers, but also the ability for thousands of small startup companies to bloom. So we've seen several tech startups from former Penn engineering students. I've got one student named Sarah who has a company called Peramble, which is building AI applications for law firms that are engaged with mass torts, where you need to examine many, many patient records to decide if a particular person was affected by a defective drug or things like that. And so she's really a small company who's accelerating the work of law firms, everything from that sort of narrow but deep application to another startup is called Martian by a pair of Penn undergrads who are building tools for model routing. So in addition to all this investment, we've seen dozens and dozens of models from OpenAI to Anthropic to open source models from Meta. And part of what you need to do when you apply this in your own business is figure out which model is going to produce the best response for the type of application you have at the lowest cost. So they're working on exactly that problem and really the foundational tool building that other companies will build upon.
So interesting how it's changing everything, especially in the startups, as you mentioned. So let's talk a little bit about how it's influencing research. So I want to ask a question of Cesar. We see, as Chris said, how AI is impacting many fields, but how has it influenced your research? Can you tell our listeners about some of your recent discoveries, particularly with antibiotics, and how you've used AI to make advances?
Yeah, sure. I still remember when I was a PhD student and I had this epiphany that computers and AI would help potentially revolutionize biology, right? But at the time, the general consensus was that biology was too chaotic, too complex for computers to have any sort of positive influence or impact on it. And after my PhD at UBC, I went to MIT, and that's when I started really implementing some computational tools and approaches. More specifically, within the realm of biology, I focus on the invisible biology, which is the field of microbiology at the micro scale. More specifically, I focused on antibiotics. And like you mentioned, my lab right now at Penn, really a lot of what we do is around using AI for antibiotic discovery. And I can tell you a little bit about how AI has really impacted our work and enabled our work in the last 5+ years. So when I started at Penn, I challenged the team with, I think, a fundamental question, which was, can we use computers and AI to accelerate our ability to discover new antibiotics? This is motivated by the fact that currently with traditional methods, it takes a long time to discover new antibiotics. So it takes over 10 years. It can take over 10 years. And it costs over $1 billion to actually do that. To put this into context, this is more than the budget that NASA or SpaceX have to take a rocket or a space shuttle to outer space. So it's an incredibly slow and expensive endeavor. And so we thought that with AI and computers, we could help accelerate this, thereby reducing the cost and the time associated with discovering new types of antibiotics. And why are antibiotics useful and important? Well, antibiotic-resistant infections, these are bacterial infections. They currently are responsible for over 5 million deaths every year in the world. That's projected to get even worse. So by 2050, it's projected to get to 10 million deaths per year around the world. And so we thought that, why not use AI and computational tools to accelerate this? And one of the things that we've been doing is we proposed this challenge, this mission to our team to mine all of biology's information to see if we could find new antibiotics encoded, hidden within biological data sets that were previously not really well mined or explored due to the lack of tools. And so we've been doing that. We've been mining. We started with the human proteome. We mined the human proteome for the first time as a source of antibiotic molecules. We found thousands of new, previously undescribed sequences and molecules there. And then we proceeded to mining not only extant biological data, but also from extinct organisms to see if we could find similar molecules hidden in organisms from the past. And so then we explored our closest relatives, Neanderthals and Denisovans. We found similar antibiotics also encoded there, and we've been really expanding everything we do to continue the goal that we have, which is to mine all of biology. By that I mean all the genomes and proteomes and metagenomes, so essentially all the biological information that we have available to us.
Cool. So you were saying 10 years to develop an antibiotic. So what is the timeline like now? I mean, so your discoveries, what was your time from thinking about it to actually being able to come up with it?
Right. So I think if I reflect back the last 5-6 years, I tend to be critical with our progress, but one thing that I think has been really surprising, and I can already consider it a breakthrough, is that now with AI, it's a matter of hours to discover thousands or hundreds of thousands of preclinical candidates. And so with the aid of computers, we've been able to completely accelerate beyond my wildest dreams years ago our ability to discover preclinical candidates that many of them are effective in mouse models of infection. And so they represent promising molecules, potential therapeutics for the future.
So now you've narrowed it down to some candidates, but then you still have to go out and test that those are effective, right?
Exactly. The computer essentially, it gives us, by now, hundreds of thousands of candidates. And then the challenge becomes, okay, how do we sort through those candidates to decide which ones to actually make in the laboratory using chemistry, so to synthesize, which ones to proceed with for testing for toxicity, safety in vitro, and then subsequently in preclinical mouse models of infection. And in order to do that, we actually utilize both computational power combined with human ingenuity. And so for every decision, we have a computational ranking. The computer basically tells us, this is the ranking of the best molecules that I predict will be great antibiotics. But then we also use human ingenuity to inform which ones are more likely to be synthesizable, which ones are more likely to be maybe toxic or have propensity to aggregate and therefore not be useful therapies. And for that, we use people in my lab, humans. We actually have something to say here. And
nice to know that we're still important.
we're still very much important. So in every project in my lab is really a tight collaboration between machines and humans. And every important decision that we make takes into account both perspectives. And I think that's probably how it's going to look like in the future. I think so.
So I think this is incredible. Like, I think the potential for using artificial intelligence for scientific discovery and advancing how quickly we can explore a bunch of hypotheses and narrow it down to a set of really successful things is amazing. And I think Cesar's work is really at the forefront of this. I feel like some of what we've seen from AI and scientific discovery is garbage, right? Like, I think some people have the impression that it's all about using a large language model to hallucinate a scientific paper that someone tries to slip into a conference, and that is literally junk science. But I think the idea of having algorithms to help propose a candidate space and then having a mixture of human-in-the-loop intuitions about which of those are the most promising to explore, along with some algorithmic ranking, is really wonderful, and I hope it gets extended to many other fields as well.
Thank you. Yeah, I mean, I do think it's essential. And in fact, a lot of the decisions that we make on a daily basis in the lab that inform the research that we're doing, they're highly weighted towards humans in many, many cases. So I think that marriage between machines and humans probably needs to continue, at least in scientific discovery and in complex, in fields as complex as biology, chemistry, and so on.
Yeah, and I love the fact that you're applying AI to data sets other than text, which is my area of specialty. Seeing it propagate from all of the data that's freely available on the internet, whether it's large amounts of text or billions of images, to other large-scale data sets. Like, this is incredibly promising, and I think we're likely to see other fields with huge volumes of text potentially benefit from these models too.
Yep, couldn't agree more.
Yeah, and I see you brought something really interesting to the podcast. Do you want to explain what this is?
Yeah, sure. So thanks for asking. Yeah, so I was mentioning earlier how a lot of the work that we've been doing has been exploring not only biological data from living organisms, but also from extinct organisms. So these are creatures from the past. And this is a protein. It's a 3D model of a protein in 3 dimensions, and you can sort of see the complexity of the protein with the different folds and the beautiful alpha helical structures. And what our algorithm did is it sampled through the protein, and by the way, this is a protein, but it's not just any protein. It's a protein from Neanderthals, one of our closest sort of ancient humans, and it's a protein called ATP synthase subunit A. That's too complicated, right? But what does that really mean? It's a protein that makes ATP, and ATP is a molecule of energy. It's a molecule that allows us to move and to operate and to go about our daily lives. And the algorithm within this very complex protein, it was able to identify this region in red that the algorithm predicted it would be a great antibiotic. It could maybe help us treat infections. And what we then did is we synthesized this fragment. So you can extract it using chemistry tools and synthetic biology tools. And we synthesized this in the laboratory using chemistry. And then we tested it against bacteria that we have access to in my lab. And it was highly effective against those bacteria. It was able to kill pathogens that are some of the most dangerous pathogens in our society. And then not only that, but it was effective in mouse models of infection. So this is Neanderthalin, and it's actually the first therapeutic molecule or useful molecule found in extinct organisms. So I'm quite proud of this and the team effort that resulted in this discovery.
So where do you get Neanderthal samples?
So as it usually happens in science, we stand in the shoulders of giants. There has been an entire field for many decades called the ancient DNA field, where many people, many men and women have been devoting their lives to trying to come up with sequencing methods that would enable them to read and write ancient DNA. And this is not easy because ancient DNA, we're talking about samples from Neanderthals that are, many hundreds of thousands of years old. And oftentimes they get contaminated. So that was a big deal for many, many years. They get contaminated when humans actually manipulate the samples. DNA from our own skin can fall into the sample and can generate contamination. Bacterial DNA can also contaminate those samples. So a lot of really smart people came up with painstakingly with sequencing methods that enable them to get a good idea of that genetic material from many, many years ago. And that field perhaps culminated with the Nobel Prize that was awarded to Svante Pavo in medicine or physiology, I think it was 2 years ago, for developing sequencing methods for ancient DNA. So those sequencing methods have then now resulted in, and that's why I say that we stand in the shoulders of giants, in a lot of data being available from ancient samples and extinct organisms. And a lot of that is available in public data sets, including NCBI, UniProt. And so all we had to do is develop algorithms, develop the toolkit, sort of the magnifying lens to go through all that information, all those proteins, all those genes, and to try to find potential antibiotic molecules.
Yeah. So, Surbhi, we've seen a lot about what AI is being really useful for, and I imagine there's many other examples. Can you tell us more about that, as well as what are some of the limitations that we should be thinking about?
Yeah, so I guess Cesar already gave a very good example of how AI has made access, made us extract so much from all this vast amounts of data that we have. So a lot of classical machine learning or AI previously required like heavy annotations on the data. Like you needed not just, raw data, but also labels on that data. And much of the success from the last decade and more recently has come from the fact that we can tap into this enormous amounts of data that has no label or no supervision and use that to learn really rich information about the structure of the underlying world. And for instance, we can take all these protein data from past and like learn something from them that we couldn't possibly do. And this has been in text for sure. Just predicting the next word makes us learn such interesting things about the structure of data. And I think what's been really exciting, is that given that we can now use language to access these models, I would say like how Google search allowed us to access knowledge, now we're able to access skills, which is very exciting that anybody sitting around can learn how to code by just using text, which is magical, right? Which is going to give so much power to everybody. So this is something that's really useful. And even the fact that you can take a large amounts of data and summarize them so well from just interacting, just giving this model a large amount of data and getting these summaries has been really exciting to see. And I've seen like really cool applications across like various domains. Like there's an NGO that I've been involved with, which has been taking all this data from legal setups in India, where we don't have enough human resources to go through all these, there are like millions and millions of cases that are pending. And it's really hard to get some human to actually go through these cases. And these AI technologies are very good with summarizing all these massive amounts of legal documents and giving access to humans to just parse through now much smaller condensed text. Apart from that, I think, which is something that's becoming more and more exciting to me, since being a math person, that I'm seeing these models do very well with reasoning. They're not perfect, but they're getting better at, taking different concepts and combining them together and being able to solve more complex problems. So that's been pretty exciting. Now we can see already these new models that people are training that are doing very well on these benchmarks on all these, exams like SAT and other exams that they're doing well on. So that's pretty exciting. Having said that, one of the biggest challenges are these models are still black box. We don't really understand them. And they often produce solutions that might seem or look really right, but if you do a closer look, they're probably not correct. And that's a big challenge because now that everybody has access to using them, they don't know how to verify them. And anything that sounds really smart, humans tend to believe is correct. And that can be very scary. So I think this is one of the biggest challenges where this is a great, powerful technology, but it's very hard to verify whether this technology is correct. So there's going to be a lot of challenges that are going to come out of this. There are technical problems and there are non-technical problems here. And I've been really excited about working on how to make these models more robust. And Penn, I think Penn CIS, we have an asset center. We have other centers that are working really hard to make these models robust. So I see a great amount of potential, but obviously a lot of challenges.
The limitations are still there. Yeah, so I teach a database class, and one of the things I do on some of my homeworks is I provide an answer to the question from ChatGPT 4, and it's wrong, but it sounds very authoritative. So I like my students to look at it and tell me if it's right or wrong. So I think one of the fears I have, and maybe you can talk about this a bit, is you mentioned coding seems to be good at. Are we going to have to know how to code? I mean, maybe our whole department just is going to fold up shop because we don't need to know how to code anymore.
Oh, that's a tough one. So to be honest, like I don't code personally as much, but with the advent of ChatGPT and Copilot, it's become so much easier for me to code now. So definitely it's going to make things a lot easier. And I would think of this as like it's augmenting my skills. I don't think it's replacing my skills. And I think it'll be still important, like how we scale, how we design. Coding is not about just solving a small problem. It's like designing these big systems and how things work, how modular our code is, there's a lot that goes on and we still need human expertise. I don't think these models are there, though they're getting better at doing the mundane, repetitive tasks really well. So I think I would see that I would want students to like learn how to use these tools to like make themselves even more powerful and more productive, and see what now maybe, put this easy work on these models and try to do the more complex tasks. So I don't think it's going to replace or supplant us, but definitely the challenges and the problems we need to solve, we need to rethink about what we can already punt to these models.
Mm-hmm. But I think the coding is a really excellent example of where the effects of large generative models is being felt by many professionals. I think initially when Midjourney and DALL-E came out, a lot of visual artists and writers with ChatGPT were worried about their careers. But I feel like the obvious place where tools are making a significant productivity enhancement is in software development. So now when you're working in an integrated development environment, like Visual Code, there'll be options from Microsoft's Copilot to suggest code completions and things like that. And I feel like this does unlock a lot of coding for newcomers. I feel like one failure computer science has had is that the entry point for absolute beginners is terrible. Like you have to overcome all these nitpicky syntactic problems where if you don't get a semicolon in exactly the right place, your program doesn't work at all, and a lot of people get frustrated and give up. And I feel like being able to program in language at first to get started is an amazing first step. Like what Surbhi was saying with the risks of things, there's also the risk of these models hallucinating, which you would think wouldn't be a giant problem because you run code and it fails, you know that there's something that's gone wrong. But I saw a news article yesterday that said many models were hallucinating the names of packages. So something that you can install to enhance Python, that's an external library. And a white hat security analyst analyzed a bunch of the Copilot suggestions and found that some packages that were non-existent in the real world were consistently being suggested. So he put a poisoned package on the place where you would download it to show that there is a security vulnerability that was previously unanticipated in proposing something that doesn't exist, and then people being able to exploit that. So super interesting that it's both a productivity tool and also a cautionary tale.
Yeah, the attacks are very interesting. Like there's a lot of people working on coming up with ways to attack these models, and these can be like just planting some data somewhere on the internet that these models train on, and that can cause these backdoor attacks, as well as like specially crafted techniques, and even using LLMs to attack other LLMs. So there's a lot of potential of attack. But yeah, these are going to be challenges that we're going to have to circumvent. But just to add to Chris brought up a really good point that the accessibility is such an important thing that, those barriers have kind of gone away once we can use language to interact with these models, that anybody can, go in and ask for generating some part of code, get this code, just run it, know how to run it, even ask for instructions on how to run it. And I've seen around my circles where people who are not technical at all have actually started getting into this space. And that's very nice that computer science is becoming open for everybody to come in and use these tools.
But I think the cautionary tale is, you were saying, Chris, that, you run it, doesn't work. That's great because then you know what's wrong. But the worst case is that it actually runs and it gives you something and you think that's the right answer. And unless you have the human judgment to be able to detect that, you're going to be having very buggy software. So I think that, the sort of the human judgment that I really like Cesar saying is, we narrow it down to a set of candidates and then we have to think deeply about it. I worry that we have to do that as well.
Absolutely. And I think your example that you give to your students of here's what ChatGPT proposed, and here's like having them understand A, that it is wrong, and then B, how it's gone wrong, I think is an incredibly valuable object lesson, not only for your students, but people generally to use these models at the moment, right? We're at the stage now where hallucination is still a big problem. It's becoming mitigated as we're introducing new techniques like retrieval augmented generation, where instead of relying only on what the model has learned and internalized in its own parameters, we'll pull in documents and be able to summarize them. Like Surbhi was saying, it's really great at that. But we're still at this point where people need to understand the limitations, and you need to have some expertise to operate on top of them to make them most effective. So I wanted to connect Cesar's scientific discovery with what Surbhi was saying about being able to summarize potentially millions of documents. And I feel like this is a path towards scientific discovery with large language models that will open it up to all sorts of different fields. So all of our colleagues, even outside of engineering and the School of Arts and Sciences, I believe in the short-term future will be able to potentially have their own research enhanced through large language models and other kinds of AI systems. So at the moment, most people interact with these systems via ChatGPT or things like that, which has a fairly limited amount of context that it can operate on. So I can, maybe summarize one document at a time. But I feel like these tools are also potentially scalable to large data sets. So some of my PhD students are working on open source packages to allow people to effectively use models for their own research. And one example is a Python package that one of my PhD students has designed to allow you to do fan-out questions. So if you have a question that involves looking over all Fortune 500 CEOs, then you need to be able to go figure out what are the Fortune 500 companies, who's their CEO, and then probably do some recursion. So I posed a question to him, like we were having some debate about whether, very wealthy people were over-admitted to Ivy League universities. So I wanted to know, okay, for all Fortune 500 companies' CEOs and for all members of the Senate, what's their alma mater and what was its acceptance rate? And I like that, just that kind of curiosity-driven question that requires aggregating over a huge number of documents, like the millions of legal records in India, or not text-based, but the huge genomic access that you could have. I think that's a really exciting direction for the future of scientific discovery with these kind of models.
Yeah, I mean, I'll just to add, we are using LLMs now for some of our approaches. A bit early to comment on that. It's still ongoing, but we are doing that. And we are also developing our own software. So for our latest work, a postdoc in my lab, he developed a deep learning model that enabled us to mine hundreds of proteomes at a time instead of just one at a time. And that has been incredibly instrumental in our ability to uncover novel antibiotics in a lot of different, basically biological data. And so yeah, I mean, I think thinking about this from different perspectives and trying to develop new algorithms is something that we're also very much excited about in my lab.
Yeah, another thing I might add, like apart from like maybe it would seem like these models are really gigantic and the access to them is restricted and it's very costly. Another thing that the field has been doing really well is making open source smaller models accessible, which anybody can download right now and with like a small amount of compute can actually run these models. And they're also pretty good at these tasks that, we would want to do. So having access to those and the development of those is really exciting because all of us can then run them on our own, on our data, how we want to run them instead of like, reaching out to OpenAI or some company to share our data and make them access it.
So it sounds like now we're not just going to have a problem with too much data and what do we do with it, but too many models and what do we do with them?
Yes.
It's going to be a recursive problem here.
There's a competition going on. Which one's beating which one?
Yeah. And I think it's also a great engineering problem, right? Picking the right model for the right task and being able to optimize models that are just the right level of computational expense for the particular task that you have. I think especially if you want to create a company where you really care about how much it costs to run millions of queries every day, like that kind of optimization is super important. And then I think this idea of systems engineering where you take a giant model and then create your own smaller special purpose built one is a super exciting direction. Another of my PhD students has just released a Python package called Data Dreamer to create synthetic data sets to allow you to go from a very large model like GPT-4 onto a much smaller one if you have a narrow task in mind. So very exciting research all over the place with lots of engineering implications.
Yeah, and algorithmic selection has been like the bread and butter of machine learning always. We are always like, we have options to choose which machine learning model we want to use for our task. And this is just like now we have a lot of these big models that we need to decide. And there's a lot of like, from theoretical studies that, I've also been part of, like we've tried to understand these computational statistical trade-offs, which means how much compute and how much data you need to make these models perform well for different tasks. So there's a lot of grounding on trying to understand which model is better. And hopefully there'll be an automated way to decide which model is the best one for your task in the near future.
And I think there's another dimension to the models that we haven't yet talked about, which is that models could be biased. They might not align with our values. They might not correspond to what we think of as advancing the greater good of society. So how do we balance that as well in this model selection process or model development?
So I think that that's one of the most crucial aspects of artificial intelligence, and it's becoming a really prominent research area. So often we'll talk about model alignment. And the alignment here, we mean modeling aligning the model's output to societal values. So because these models are trained on data gathered from the internet, they often encode and even magnify negative societal biases like racism and sexism. And so we actually have to take active steps to mitigate against it. And so the subfield of AI called alignment is trying to do that. And we're still learning what's the best way of doing it. So we saw a misstep by Google with its Gemini program where it got a lot of flack for overly... So the misstep was if you typed any prompt into Gemini's text-to-image generation, it would try to create a racially diverse group of individuals. So I think it's clear where that's coming from. If you type in, I want a picture of kids doing math or kids who are good at math, you don't want it to just be a room full of white and Asian boys, right? You want it to reflect the diversity in aspirationally how we want mathematics represented in the future, and that should include everyone. So because you have models that adopt and magnify societal biases like boys are good at math, you have to mitigate against it. But because Google was rushing to market, they did prompt rewriting in a way that didn't select among which images they should add this kind of racial diversity to. So you could type in things like, give me a picture of the founding fathers, and it would create a much more racially
diverse
it'll include women. And I think that that's awesome if you're Lin-Manuel Miranda and you're producing Hamilton Part 2, perfect. But if in terms of historical accuracy, it felt like a little bit of a misstep. So I think that their heart is in the right place and that it is a necessary step, and I don't want to knock Google for trying to do it right, but it is a complex issue that we're still navigating.
Yeah, and a lot of solutions have been pretty ad hoc, RLHF and other kind of techniques that alignment has come up with, and then it's a hard problem. Like it's really hard to fix this by just adding a prompt, and this is true even for DALL-E. I mean, I try to generate a lot of images for my talks from DALL-E, and we get the same problem. Like it tries to be accurate, like whatever like the person has encoded into the prompt, that add diverse images, add more than one object, or like things like these kind of soft prompts, but that's not enough to solve this really complicated problem. So I think there are like really exciting challenges on how we can align these models, and a lot of teams are working actively. And in fact, like I'm part of organizing this workshop, this actually special year of large language models and transformers at the Simons Institute, where we're bringing together a bunch of people from very core theoretical computer science as well as natural language processing and other areas to sit down and think about how can we build the foundations of these models to be able to answer these questions, even formulate what the guarantee we want here is. So I'm pretty excited about it.
Are there also ethical issues? And I don't even know.
I mean, I completely agree with what my colleagues have said, but the way we think about this in our own research, so one of the things that early on I started worrying about is when we're initially unveiling all these molecules from extinct organisms, one of the things that I started thinking about is what does it mean to resurrect these molecules, right? Because a lot of them, as far as we know, they're not expressed in living organisms today. So they're not present in the biological world around us. So what does it mean to resurrect some of these molecules and using chemistry and bringing them back to life, if you will? Is that okay to do that? And so we've been consulting with bioethicists, people that know a lot more than I do about how to do this well. And one of the things that we always advocate for is to innovate responsibly. So, for example, one of the things that we've been doing is making sure that the sequences, the small proteins that we work with, they don't have an ability to self-replicate. So in case they would escape from the lab, they would be able to self-replicate in some way. But obviously they're not living organisms, right? We work with proteins and peptides, which are small proteins. And so they're really quite safe, like in the sense that they can't really, they can't live on their own. They can't really replicate unless they have these self-replicative sequences. But we've been thinking deeply about that. You know, what does it mean to do a lot of the work that we're doing, and how do we ensure that we do it responsibly moving forward? The other kind of ramification of some of this newest work from the lab. It was on the patenting side, which I thought I think maybe I just mentioned it. But when we were initially discovering some of the sequences from past organisms, I went to the patent office at Penn here at PCI, and I told them, I know that natural sequences are not patentable, right? Like natural sequences that you can find around you, they're not patentable. This is due to a case called the myriad case that determined that these were all for everybody because they were part of nature, and nobody could claim a patent on them. But I asked them, what about sequences or molecules that used to exist hundreds of thousands of years ago or thousands of years ago, but are no longer present in nature today? And I think they thought I was crazy when I asked that question. So I had to tell them a little bit more about the project and what I was talking about. But this has actually opened a new area of patent law where lawyers are trying to figure out whether these things might be patentable or not. And I've recently written an opinion piece with a patent lawyer to think about this problem from a bioethical and patentability perspective. And I think it's just another example of how AI is opening up all sorts of new avenues that were completely unexpected when we initially started this work, at least. But it really aligns with what my colleagues are saying, that AI really is revolutionizing many domains of our society, and bringing up new issues, challenges that I think are incredibly interesting. And I think we just have to be optimistic and be proactive about tackling them.
And I think the really interesting thing is it's causing us to reach across disciplinary boundaries to interact with other people like bioethicists and lawyers. There's other types of misapplications of artificial intelligence that's raising a lot of concerns at the moment. So one example is, being able to do voice cloning or deep fakes of people's images. And we saw in one of the primary elections that someone voice cloned President Biden and broadcast a message saying, don't go out and vote in the primary, which is obvious political malfeasance. But then even there was a case just recently of a Penn undergraduate who has a YouTube channel, and her image was cloned and just used to sell products, just random stuff where it's unclear why she was picked out of all these, influencers as the person that someone just misappropriated. But that's also caused me to reach out to other people and talk about aspects of law that I've been previously never exposed to. So there's the world's expert on the right of publicity, which governs how your likeness, including your appearance and your voice, gets used here at Penn's law school. Her name is Jennifer Rothman, and she's written a marvelous book on the right of publicity. So I've been in conversation with her, trying to understand the legal framework that exists for this kind of law, and then also talking with policymakers, having consultation with Senator Coon's office about a potential national right that would govern these fake AI-generated images. And I feel like it's super important both for us to be able to act ethically and to guide our students in a way that their education is going to contain that as a foundational component, but also in us trying to help shape the narrative and the national policy and, as our students graduate, to shape company policies in places that they'll have influence as well.
One thing that I maybe might add is also there's a concern that AI might lead to bioweapons, and so within the field of biosecurity, there is such a concern. So there have been a number of workshops being organized by one of them colleagues at the University of Washington, and I recently signed a petition or a letter asking asking for some sort of guidelines so that bad actors don't utilize AI in ways that can lead to generating bioweapons that can be obviously deleterious to humanity. So that's another thing that maybe within the realm of biology and the things that I work with, I think might be worth sort of thinking about.
Yeah, absolutely. And I think that's another place that there's crossover. So I went to the OpenAI Developers Day, and I met with one of their employees who works on trying to anticipate what are the misuses of AI systems and whether they have the capabilities. And that was actually a use case that she was discussing is how would you even understand whether a model that hasn't been tested in the world could enable a bioweapons attack or enable an actor to more efficiently create a bioweapon than they would just searching the internet. And it's a really important, low probability event, but incredibly important to think through. And I'm glad that there are people who are concerning themselves with these questions.
Just to tie this back to what we can do as professors or teaching students, I think it's really important to imbibe responsibility to the students who are going to use this technology. So the course that I teach in machine learning, it's an intro to machine learning course. We end with a lecture on discussing the ethics behind these systems and the power that you have when you build these systems, so that if you're not necessarily, when we teach computer science, we don't necessarily teach the social science of or the other adjacent fields of ethics and other things. So it's really important for students to understand when they are bringing in technology, what impact they can have. And I think we all can play a big role in trying to make the next generation be more responsible with what power they have.
So since you've brought the conversation back to education, let me ask a question of Chris. Penn Engineering recently announced that we're the first Ivy League to offer an undergraduate degree in AI. So tell me, what does this degree look like? How does it compare to, say, a degree in computer science? And how does it affect the degree holder's future job opportunities?
So I think we all recognize that AI is having this really large, disproportionate impact on the world, and we anticipate that that's going to continue. So we've been able to put together this really exciting undergraduate curriculum that's a joint effort between the departments of computer science and electrical systems engineering. We've designed it in such a way that students will get a really superb foundations in the algorithmic, mathematical, and ethical foundations that they'll need in order to make advancements in artificial intelligence. So I'm incredibly excited by this program. I think that it's coming out of engineering gives it a particular flavor and mathematical rigor, but I've also been trying to ensure that we have a broad approach to artificial intelligence and that we not forget the societal implications, the policy implications, and also that we not neglect the fact that our colleagues in arts and sciences have been doing a lot of incredible research over the years in cognitive science and neuroscience that could potentially help inform AI models as we go forward. So I think this is a wonderful, wonderful degree program. If I were an undergraduate entering college right now, this is what I would be aiming to take. So I'm super excited that we're launching it and doing so in such a quick fashion in response to the pivot that everyone's making into artificial intelligence.
Yeah, so it's. I would just like to chime in and say that, being a new faculty in Penn, where Penn is growing so actively in the area of machine learning and AI, makes this a really exciting place. I'm really excited about the opportunities that I have to collaborate across departments, maybe 5 departments or more, and bring about real impact and make lives better. And I think there's no better place than Penn, where we have such strong departments and such strong faculty and even stronger students who are so excited about AI. And now we'll have our AI undergrad program, which will encourage people to even more think about AI. So.
Yeah, just to add, I do think that Penn is a mecca for AI, and anybody that might be listening to this, thinking about coming to Penn, if they want to be at the forefront of AI research and innovation at the academic level, I think this is probably the best place in the world right now.
Great. Well, thank you all so much for your time and for your insights. This has been a very exciting panel. I've enjoyed listening and learning from all of you. I'm certainly certain that our listeners have also learned a lot through discussion. And I want to thank our audience for joining this Penn Engineering Innovation and Impact podcast on AI. Please subscribe to Penn Engineering's Innovation and Impact podcast series on your favorite podcast platform and watch the video of this recording on Penn Engineering's YouTube channel. We'll see you next time.